Okay, this is the 10-5 notes for statistics honors. Just a side note here that we don't do section 10.4. So if you're wondering why we skipped it, we don't cover that. It's not in the curriculum. In section 10.2 and 10.3, though, we talked about inferences for two population means and the fact that we were dealing with independent samples. Now, what would happen if these means were coming from dependent samples? We call those dependent samples paired samples. So this next line here actually describes it pretty well when we use paired samples. It says we would use a paired sample whenever it is clear there is a natural pairing between respective members of two different populations. There's a lot of different ways to interpret that, but generally the idea is let's say someone was taking a pre-test and a post-test for some scenario. So before they went into a course, they take a pre-test to see what they know, and then once they're done with the course, they take a post-test to see what they've learned. We would consider that would be a paired sample because it's the same person taking the test, which means in reality, the probability of that person performing on the post-test is definitely dependent on the pre-test, depending on what they know and so forth. So that would be a good example of that, whereas in all the other examples we did in previous sections, the two groups had nothing to do with one another and no bearing on one another. So we were using pooled or non-pooled procedures at the time. So now we're going to be using something called paired procedures, which are going to be specifically for whenever we have dependent samples taken from two populations. Okay, again, the first thing we always do is we talk about the sampling distribution for some paired scenario. So if that's the case, basically our t is going to be this formula right here, our t statistic. So no z's in this section again, but just a t. So what you're going to see is something vastly different from before when we talked about independent samples. So we basically have this setup where we have something called d bar minus mu1 minus mu2 over s sub d divided by root n. So what I'm going to do basically underneath this is I'm going to talk about this formula and what it all means. Okay, so what is d exactly? So d is called the paired difference variable, and it represents the difference between every pair of means. Okay, so what are we going to be doing? We're basically, once again, going to have two data sets. And the key, though, is we're not going to treat them separately. We're going to treat them together, which means we're going to take every pair of data and we're going to subtract them to create a difference. So there will be a D for every paired piece of data in your data set. So D bar logically means we're going to take the average of that difference, and that is the value that's going to go right here in our data. Now, luckily, we know what's going to happen here again. So when we do the null, it is going to be a scenario where these two are the same, which means that's once again going to become 0, and all we're going to have is d bar in the numerator. Second thing, S sub d represents the standard deviation of the paired differences. So that's this guy right here. So how do we compute that? We compute it using this formula right here. This formula is actually very straightforward. It's similar to other standard deviation calculations in which we can use a table in order to find the sum of d squared, and then a similar table to find the sum of d, and then that number squared in terms of the values. So there are the calculations themselves are not so bad. Students usually don't have a big issue with these calculations. But you can see that everything is going to be a little different. Now, as always, the easiest way to really understand this is to do an example, so let's do that. Okay, so what exactly are these paired differences and how do we find them? Well, let's look at an example. It says the U.S. Census Bureau publishes information on ages of married people in current population reports. Suppose that we wanted to decipher whether in the U.S. the mean age of married men differs from the mean age of married women. A random sample of 10 couples is taken in the scenario. Okay, so if you look over on the right, basically we have 10 couples right here. So we have heterosexual couples, of course. So we're going to have husband-wife couples for each, and then their ages for each of them. So in the first couple, just to make sure everybody understands, we have the husband's 59 and the wife's 53. In the second couple, husband's 21, wife is 22, and so forth. So these are considered dependent samples because the husband-wife create a dependent pair associated with one another. So therefore, in this scenario, we would stick to what's called a paired, sort of paired procedures, essentially. So just to be clear, this has nothing to do with pooled. I know pooled and paired kind of sound similar. They literally have nothing to do with each other, so just be aware of that, of what's going on. So just as a summary over here, I put some important concepts. It says, this is an excellent example of a paired sample because married couples are ideal natural pairing. Though using independent procedures here is technically okay, using pair procedures ideally removes the source of variation in the ages of the married couples. So this is a scenario where we could have used independent, some you can't, but it makes more sense here to use paired because they're a natural pairing. It says, in order to proceed with paired procedures, we must find the paired difference variable for every husband-wife tandem. Do so in the table. So how do we do that? Well, we're just going to do husband minus wife. So if we do so, we're going to get 6 for the first one, -1, -3, 4, 6, -2, 1, 4, 13, and 8. So each one of these are technically an example of D, okay, a difference between them. So the key, though, is in our formula that we're going to need soon is we need to know D bar. So that means we need to take the average of all of these guys. So the first thing we want to do is take the sum of all the individual Ds. So that's going to be 36 if we add them all up. And then to find the average, we have to do 36 divided by how many there are and get 3.6 for D bar. So what does that mean exactly? That means that the average difference in age of husband older than wife is 3.6 years. So let's take a look at what the procedures are for what's called a paired t-test. Okay, a paired t-test is going to be a little bit different. We already talked about how the formula is going to be different, but you're going to see some differences in the assumptions. So 2 assumptions, basically, we have simple random paired sample, and we have normal differences or a large sample. Okay, so just a note here, do you notice that there is a singular large sample here? So the key is that we are concentrating on not the individual 2 samples. We're concentrating just on the difference. That creates 1 sample that we're analyzing. So this is vastly different than our pooled and non-pooled procedures where we were treating each one of these data sets differently. They're separate, we tackle them differently. We care about just the different sample in this scenario. And yes, this is a randomly set of pair of couples, so that is good. And the one thing, though, it's interesting about our problem is that there's only 10. So in this scenario, we're going to be like, wait, do we actually have this? Because it doesn't say anything about normality in the original problem. We'll tackle that in a second. The null and alternative hypotheses, fortunately, are going to be the same in terms of independent versus dependent tests. So again, it's always going to be a statement of equality for the null, and then whether it's not equal to, less than, or greater than the alternative. Here's your test statistic that we'll be dealing with. Remember, the U1 minus U2 has been removed. It was to the right of the D bar. If we go back up here, it was right here. This has been removed because we know, again, that the assumption is that that's going to be 0 in the null hypothesis. Okay, so a small thing here. So getting back to the normality, let's do, well, before that, I'm going to read this. It says, returning to our age of couples problem, at the 5% significant level, do the data provide sufficient evidence to conclude that the mean age of married men differs from the mean age of married women. Okay, so by now you should be experts at locating the key words. So clearly we have a differs, which means this is going to end up being a two-tailed test eventually. We'll tackle that in a second once again. But before that, we want to talk about these assumptions. We talked how we do have randomness, but do we have normal differences? We only have 10, so I'm going to read this. It says, if you look at the assumptions for the paired t-test, we already have a random paired sample, but our sample is not large enough to quickly make an assumption of normality. And to be clear, we are only looking at the distribution of the paired differences to see that it is normal. We are not looking at each husband-wife distribution like we did for pooled t-tests. So what I did here was I produced a normal probability plot of just the differences, right? Just the differences. So you already know how to do that in your calculators. You can put it in L1 the differences, and you can go from there with a normal probability plot. Remember NPP, we used it. So if you look at this, what are we always looking for in a normal probability plot? Some type of linearity, and it does appear like there isn't a big pattern. It looks like we're okay to decide that this is going to be normal. So once we have that decided, we can move on to the rest of our paired t procedures, which we see, of course, here. Okay, so it says, before we get to the test statistic, though, let's compute the standard deviation of the paired differences, which will be required for that. So this is actually similar to our pooled procedure and the fact that we could not calculate t unless we found the pooled standard deviation. Well, now we can't calculate t unless we find the standard deviation of the difference. Note, we already know what d bar is. It's right here. So that's good. And of course, we know the sample size, so SD is going to be the important thing in order to figure this guy out. Okay, so let's find this paired difference, so or this standard deviation of the difference. So we got S of D is equal to the sum of D squared minus the sum of D quantity squared over N divided by, still in the radical, n minus 1. Okay, so we actually know one of these already. So over here in our chart, we found that the sum of D is 36. Well, what didn't we find? Well, we found the sum of D here. Sum of D is 36. What do we need in order to find this? We need the sum of D squared. Okay, well, let's go back to the table and work that out. So if you go over on the right over here, what if we need a D squared row? So all we have to do basically is square each one of the values of D, 36, 1, 9, 16, 36, 4, 1, 16, 169, and 64. Just verifying this. I did mental math here. 36. Okay, we're good. So our goal is now we need to find the sum of the D squareds, which is going to be 352 if you throw this in a calculator. Okay, so if we go down here, this is 352. So this will allow us right now to be able to simply sub in the formula. So over here, the sum of D squared is going to be 352. We want the sum of D quantity squared all over 10. And we want to divide by 10 minus 1. This is going to give us approximately 4.971. So we do have the standard deviation of the difference, so we will be using that when we calculate the test statistic in the next step. All right, so let's calculate the null and alternative and compute the test statistic. So as stated, our null is always going to be a statement of equality and will always be the same. Mu1 is equal to mu2. And the alternative, we talked about how the word differs was the key word right here in our statement. So that means we are going to be doing a two-tailed test for our hypothesis test. I do want to point out that if you look in other textbooks, the null and alternative for a paired t-test can be different. I know that I don't want you to go in that direction. I want you to be consistent with the book And I'll even say that I learned it differently when I was in school, but doesn't matter. For the sake of doing homework and everything, we want to keep this streamlined. So I'm just warning you in case if you're struggling and you start looking this up in a textbook or Google it or something like that, you might end up with something a little different, but we'll stick with this. So we just have to do the t-test statistic. So remember that's equal to d bar over s sub d over root n. D bar we calculated to be 3.6, so just as a reminder, right here, 3.6, right? Okay, S sub D we calculated right here to be 4.971. And we have 10 couples, so we divide by 10 in the denominator. If you do this math, you're going to get 2.290 as your t-test statistic. Okay, so let's take this t-test statistic and follow one of the critical value or p-value approaches, which is exactly what we've been doing in every other section. Remember, the only thing that ever changes with these approaches is how we determine the degrees of freedom when making a decision. Remember when we were doing the pooled, it was n1 plus n2 minus 2. When we were doing the non-pooled, we had the crazy formula for delta. And now we're returning to the old school n minus 1, where n is the number of paired samples. So in the last time, I think in 10.3, we did the p-value approach first and the critical value approach second. So why don't we just reverse that? We'll do the critical value approach now just to do something different and to get you more practice with each one of these approaches. So how do we conquer that? Remember, we start with alpha, which is 0.05. Since we're doing a two-tailed test, we are going to need alpha over 2, which is 0.025. And of the degrees of freedom is going to be 10 minus 1 for our 10 couples equals 9. So remember, this is a two-tailed test, so we're going to have two markers where we reject in the tails and do not reject in the middle. We need to find negative t sub 0.025 and positive t sub 0.025 at, it looks like 9 degrees of freedom. So if we go to our t-test here, let's get rid of the old stuff here, at 9 degrees of freedom, t 0.025 is going to give us 2.262. So we got, close this, negative 2.262 and positive 2.262. Okay, this looks a little funky, so I'm going to clear that up. Okay, so then we take, as usual, our test statistic, which we just calculated above here to be 2.290. We place it somewhere on the chart. This is actually a pretty close call here, but you get t is equal to 2.290, just about right there, which means that even though we barely reject, we are going to reject h naught in this problem. So just as a summary, what does that mean? Well, our null hypothesis right here implied that the ages of the husband and wife are the same. So this basically says that if we reject that, then we are saying that they are clearly going to be different, which will be our overall conclusion for our resulting problem. Okay, so we're going to do one more example here of a paired t-test, and this one's going to be very important because we're doing all the math at once, all the analysis, so you get to see how it all comes together in our problem. It says a shoe manufacturer claims that athletes can increase their vertical jump heights using the manufacturer's training shoes. The vertical jump heights of 8 randomly selected athletes are measured. After the athletes have used the shoes for 8 months, their vertical jump heights are measured again. The vertical jump heights in inches for each athlete are shown in the table. At alpha 0.10, is there enough evidence to support the claim? Assume the vertical jump heights are normally distributed. Okay, so what are we looking at? Well, first of all, assumptions. They clearly say that we have randomly selected athletes, so that's good. And we have a claim of normality, so that's really all we have to go by here. The big thing, the big decision-making process after this is literally about what type of test to use. So we have two data sets right here. So we are using, an inference with two population means, but the question is, do we keep them separate and either pool or unpool them, or non-pool them, whatever the word is, or do we combine them and pair and make a paired sample? Well, the key is that we have the same person jumping before and after with these shoes. So if it's the same person, then the jump is dependent on the from before and after, which means these are by definitely dependent heights that are being calculated, which means this must be a paired sample. There is no argument about this one. With the husbands and wife ages, there could be an argument for doing that separately, but with this, there just cannot be. These are dependent samples, therefore we must use a paired t-test for our scenario. Okay, so what does that entail? Well, let's start with the null and alternative. So we got always mu1 is equal to mu2. So we're going to represent vertical jump heights before for 1, vertical jump heights after for 2. Alternative, again, be careful. So they're saying can increase. So the new shoe can increase the vertical jump heights. So they're saying that this one here should be higher, which means this one should be lower, which means we're thinking that mu1 should be lower than mu2. So just be very careful with that, because again, I've already given you a ton of examples of this, but you want to always be aware that just the testing can be very difficult, or the alternative can be very difficult to kind of figure out. Okay, so before we can do anything, we have to work on this table, correct? So if we look over at the vertical jump heights, we need a D. So now we're in rows, so we're just going to stick to rows. We are going to subtract top minus bottom and get -2, -3, 0, -1, 2, -2, -5, -3. We are going to take the sum of that, and we are going to get -14. And we're going to also find the d squared column. That's going to be 4, 9, 0, 1, 4, 4, 25, and 9. And we also need to find the sum of the d squared, which is 56. These are all values that were in our table. Also, once we know this, we also need to know d bar. So d bar, there are 8 athletes, so we're going to do -14 divided by 8, which is going to give us -1.75. Okay, so that's everything we need in order to accomplish what needs to be found. Recall that we can't find t yet. We first have to find the standard deviation of the difference. That is equal to 56, which is going to be our sum of d squared minus our sum of d, quantity squared, over n is 8 in this problem, over, still in the radical, 8 minus 1. If we do this calculation, we're going to get 2.121 as our standard deviation for our difference. We can find t, so t is going to be equal to the d bar, which is -1.75, over our standard deviation of the difference divided by the square root of our sample size, 8, which is going to give us -2.334 approximately. So we have everything we need. So remember what I mentioned was, so in this one I did critical value just to switch it up. So let's go back to p-value, make sure that is all good for what we're going to do. So basically for p-value, we have t is equal to -2.334. We're dealing with a left-tailed test, so p-value is out here only. So how do we find that? P is equal to, we have our really small number, -1e99 to -2.334. With 7 degrees of freedom. So how do we know there's 7 degrees of freedom? because DF is equal to n minus 1 now, 8 athletes, which means 7. So we're going to get approximately 0.0262 as our p-value. So what are we comparing that to? Well, if you look, alpha was actually 0.10 in this problem, so 0.0262 is clearly less than that, so we are going to reject H naught as our conclusion. So what does that mean? Our initial statement stated basically that the heights would be the same for both shoes, so we are rejecting that and stating that the shoes would help in determining that would be jumping higher in this scenario. Okay, last thing, our paired t-interval for this. So a confidence interval for these paired scenarios. So assumptions are the same. We look at our formula here. A very simple formula. Basically, we're taking our d bar, which we already calculated for our different examples. Remember, t sub alpha over 2 has always been the same no matter what 2 population procedure we had. And then SD over root n is our usual denominator value for our test statistic that we'll go over next to the critical value for t. So what I did basically is I just returned to our first example where we were talking about the ages. So remember when we were talking about this guy here, we determined that the paired difference was 3.6, and we calculated the standard deviation of the difference to be approximately 4.97. So I brought those values back into our problem here so we didn't have to recalculate them right here. So we're going to find a 95% confidence interval. So what do we need to do? Well, again, our confidence is 95, which means our alpha is equal to 1 minus 0.95 or 0.05, which means our alpha over 2 is 0.025. Our degrees of freedom is equal to 10 minus 1, which is equal to 9. Okay, so if in that scenario, if you recall, we found actually what t alpha over 2 at 9 degrees of freedom, the critical value is actually right here. That is going to be the same value that we're dealing with in this one. So just as a reminder, the formula above, I'm going to rewrite it. So d bar plus or minus t sub 0.025 times s sub d over root n. So if we calculate that, we're going to get our 3.6 plus or minus our 2.262 times 4.97 over root 10 for our 10 couples. This is going to give us, this side is approximately 3.554, which means our interval is going to be 0.046 to 7.154. Okay, so if we were to summarize that in a statement, interpret it, we would say we are 95% confident that the difference in age for married couples is 0.046 to, actually, let's do this. I like the between word better. Is between 0.046 and 7.154 years. Okay, so obviously again, so as stated, so this is years. These are in years, right? So what we're dealing with. Okay, so as we have done in every single section so far, we need to just talk quickly about how we can relate a confidence interval to a hypothesis test. A little repetitive, but very important in terms of being able to do this. So if you recall, in the husband-wife age problem, our known alternative was mu1 equals mu2, and mu1 is not equal to mu2. So again, we have a two-tailed test at alpha 0.05. Okay, so look at our 95% confidence interval. Note the sum of 5 and 95, 1 or 100%, which means if we have 100%, that means we can use this interval right here to make a decision about this test. How do we do that again? Well, if in this scenario, this is implying that mu1 minus mu2 is 0. So we need to look on our interval and see if 0 is there. Clearly, it is not in the interval. If 0 is not in the interval, then we basically are concluding that this cannot be true, and we reject H naught. So if you return to our problem way back when, so we did our paired t-test, age of couples, we went through it. Remember that our ultimate decision was to reject H naught, which means, again, we can use this confidence interval as long as the variables match up and the percentages match up with a two-tailed test. We can use it to make the same decision for our scenario.